So, welcome back students. So, this week or this lecture will be talking about a very novel transformation is named as pi-cationic cyclization. It is not a name reaction, but it is a very useful transformation. You can call it as a transformation, very important transformation. And if you see, we have given a target molecule. Okay. It is definitely a complex structure and is a complex carbocyclic skeleton. There are 4 rings are involved here, and as I said, this pi-cationic cyclization as a unique transformation will try to explore how different strategically useful retrosynthetic disconnection will help you to come to this final target. We initially draw a retrosynthetic arrow and show you what are the possible bonds will be basically disconnecting it. First, let us draw the core structure, keeping in mind these things will be here, and the right hand side you have a O methoxy here. We did not put the double bond here. We say that this double bond will be generated from a 1-2 elimination of a carbocationic species, something like this. Now, this carbocation will be normally formed if you have a paramethoxy, means paramethoxy benzyl cation. So, this carbocation is normally stabilized by this OMe group. So, this could be a one of the. So, first retro we are basically making this double bond. This hydrogen will then try to eliminate to give this molecule, and as I said, the driving force is the paramethoxy benzyl cation is normally stabilized by this paramethoxy group electron releasing factor. Okay. So, this was the next retro. The next retro is crucial, you check it carefully. Next retro will be trying to figure it out, making the central ring. They said there are 4 rings, and now we will try to put a carbonium ion on this carbon. So, we are basically disconnecting this particular bond. Now, what is the driving force? The driving force is a tertiary carbocation. Now, how this tertiary carbocation will lead you this intermediate ended to this target, means that this pi bond will undergo cyclization, because pi bond is electron rich, and once this pi bond pushes its electrons to quench this carbocation, you get this carbocation. So, it is like that is why its name is pi-cationic cyclization. The carbocations will be generated based on its stability, and in close proximity you have a pi electron. So, pi electron will try to stabilize or try to pushes its electron to quench the carbocation. So, this is the one of the intermediate. Next intermediate, which will be now drawing, see it very carefully. The stepwise demonstration of how a complex structure can be thought of. Now, we say we will try to put a carbocation here. Now, we will put a carbocation here. So, This is again a 3 degree carbocation. Okay. Now, try to put the arrow. This carbocation is in close proximity with this pi. So, if it closes, it will give a carbocation here, which is basically here. Now, this pi electron will undergo electron shuffling to this carbocation, it will get a para-methoxybenzyl things. So, stepwise carbocation will be generated and will undergo cyclization. So, this will be now we will try to figure it out the what will be the suitable starting material. Put 2 methyls here and then you try to formulate the or try to figure it out the remaining ring. So, eventually all the 3 rings we basically disconnected. Now, this cyclization is pretty important. So, eventually if you have this compound where 3 different pi bonds are there. Now, these 3 different pi bonds are basically positionally situated in such a way it is in close proximity to this carbocation. So, this compound if you just if this is a starting material or starting precursor, you just subject to a H plus like standard way you do a Markovnikov reaction. So, these things will generate this stable carbocation because it is a 3 degree carbocation. Now, this 3 degree carbocation will get this pi, it will try to quench it here, will give you a carbocation here which is this, and then you basically get another pi electron, another pi cloud here, and that gives you this para-methoxybenzyl thing. So, eventually your whole process basically you now need something like this. And now, if you try to do a retro that which will be the starting material or where from you access the starting material, you will find that this starting material can be is a CH2 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 CH2. You put a MgX kind of thing and then so, if you have this particular carbonyl compound which is basically 1, 2, 3, 4, 5, 6, 6 methoxy, 1 tetralone, 6 methoxy, 1 tetralone. Now, this 6 methoxy 1 tetralone will trying to do a Grignard reaction CH2 CH2 MgX. It will basically give you OH and this CH2 CH2. Then you do a simple 1-2 elimination of this alcohol and this hydrogen, that will basically give you this starting material. So, simple starting materials like this ketone and this Grignard. Now, this ketone has this 2 ring. Now, I name this ring 1, 2. This is basically 1 and this 2. Now, ring 3 and ring 4 will be formed during our pi-cationic cyclization. So, first take the starting material, react with this Grignard and do the elimination, will basically coming to this part. Okay. Now, you have a 3 pi electronic things, 3 pi bonds. Now, you subject to this to a mineral acid, initially you get this 3 degree carbocation. This 3 degree carbocation is normally stabilized, very stabilized tertiary carbocation as all of us know. Then this 3 degree carbocation you get this particular pi olefinic unsaturation. It will try to react in this way to give you the ring 4, the ring 4 is this one, and you have a newly generated carbonium ion which is again a 3 degree Okay, this one. So, ring 4 was already formed, this is ring 2, this is ring 1, and then this carbocation will try to react with this pi to make you ring 3, ring 3, ring 3, and finally, you will find that this gives you a para-methoxybenzyl carbocation, which is also very much stabilized. So, if you check this entire pathway, you will find that this is a very useful transformation, and as I said, this reaction is named as pi-cationic cyclization. The cyclization takes part in one pot operation. No need to isolate any intermediate, you just subject the initial starting material which was just drawn to you in the earlier slide, this one, you subject to mineral acid and then you keep on doing this reaction. So, this is very important reaction, pi-cationic cyclization, and that was normally used by our mother nature. Our mother nature uses this pi-cationic cyclization as a unique transformation to synthesize many of these natural products, particularly these natural products or this kind of structure was available in the nature, it is basically a steroid framework. Now, this kind of compounds are natural products, and you will find that in mother nature it often uses this kind of simple pi-cationic cyclization. Nature does not use the very sophisticated reagents like, as I said, dibal, LH and other oxidizing agent. Nature always uses very simple chemistry. Nature has these normally enzymes, and this kind of enzymes are basically known as cyclase enzyme, cyclase. These enzymes react as I shown, it is a sometimes you can call this reaction as cascade cyclization. Cascade, the terminology basically means that one after another, one after another. It is a one pot reaction, and eventually the chemical logic is very much clear. Chemical logic says that the stable carbocation will be generated, stable carbocation will be generated, and the stable carbocation will try to react with this pi cloud, and then at the end we will basically getting the final product. So, the entire situation is as I explained in the thing. Next, we will try to visualize something else. Before that, I will give you a simple molecule. This molecule is tetrahydrothiophene. Okay. Now, I said, is it possible to synthesize this molecule from this tetrahydrothiophene? Now, what is this? This molecule is basically butane, N-butane. You may say that, sir, if you can remove this sulfur, this is done. You need to remove the sulfur and you need to basically get rid of this sulfur part. So, essentially the reaction is basically a desulfurization reaction. Desulfurization reaction, and in reality this reaction was very efficient. It was done by Rennie nickel, is a active species which have been commercially available. Rennie nickel is a nanoparticle form of nickel, and you using the reaction in a ethanolic solvent, sometime you can use the hydrogen as a gas. Basically, now Rennie nickel is strongly thiophile. Thiophile means it has a strong interaction or strong attraction towards sulfur. The mechanism was not very much well established, but people propose that probably a diradical pathway might occur, which is further quenched by hydrogen or the ethanol which was used as a solvent to give you the butane hydrogen. So, this particular reaction it is called reductive desulfurization. Reductive desulfurization is a very unique transformation, and next we will be using this transformation for a given target. So, this information will be useful for you, that we will be using reductive desulfurization for our next target. Now, let us draw the target molecule. This target is little bit complex, but nevertheless you try to get the target very efficiently. This is a natural product. And this natural product was basically named as juvenile hormone. And actually, juvenile hormone is a natural product which was existing in many of the insects when they are in juvenile stage, means they are just born, and this particular compound act as their growing. This compound helps to grow them, that is why it is named as juvenile hormone. Now, so this target molecule will be using a transformation which we just now explored, is called reductive desulfurization. Before that, we will just cut the molecule in a very simplified fashion. This molecule, if you see the structure, it is having a epoxide at one end, and one end is having a alpha beta unsaturated ester. In between, the molecule has a 1 pi electron here, and there is a methyl, this is a methyl. So, this is the structure. So, now do a standard retro. Okay, you are having a ethyl here, another ethyl group is there. So, we will try to do the retro. And we say this molecule can be accessed from this kind of compound. Now, how? If you now analyze the molecule, final end is one allylic alcohol. So, allylic alcohol can be oxidized to corresponding acid, and then acid can be transferred to corresponding ester by a simple FGI. Okay. Now, if you have this compound or this compound, there are 3 double bonds, 1, 2, 3. Probably these two, the central one, this one and this one is more electron rich, because it is highly substituted. Okay. And the left hand double bond is sterically less congested. So, probably after this allylic alcohol, if you do a oxidation and esterification, now this double bond becomes electron deficient. This is electron rich, this is electron rich. Then selective epoxidation can be done here. We will discuss this one later on. Before that, now we explain our key strategy, which is very much important. We will try to now use the reductive desulfurization chemistry, which we just now explained in the earlier slide. We called here, we will be using a transformation based on reductive desulfurization. Now, how? You see this things ethyl, if you now try to cut this bond and this bond. By removing the sulfur, you basically get CH2 dot radical, that will be quenched by this ethanol or hydrogen to give you ethyl here, and this part you will get a simple these things. So, this is basically your sulfur part. We will just try to put here. This will be another ethyl and you are putting another sulfur here. Okay. So, these two steps are basically, these reductive things are absolutely important, and until unless you know this transformation is very difficult to analyze. Fine. So, we are here and then will be cut down the molecule to a further simplifying structure. We will try to use the same chemical analogy. This is one of the intermediate we say, and then we say that you take its structure, the final structure or this structure, but basically trying to give a retro here, and then we will basically say that we will try to introduce this part through this X could be bromo or chloro or iodo. Now, how this sulfides, these cyclic sulfides, there are hydrogens here, you can easily abstract them by simple base, because it is a close to electron withdrawing sulfur as well as the allylic. So, this is a nucleophilic center and you can really react with a allylic halide as a electrophile. So, this is our initial reaction, and then this compound. So, this is basically one of the starting material. Now, this bis tetrahydrothiophene or dihydrothiophene you can easily prepare starting from this compound. We will explain how, and this initial starting material was basically prepared from a compound like this, a cyclohexanone analog, where the 4 position the CH2 has been replaced by a sulfur group. So, this is the starting material which will be using as a commercially available cheap starting material. Now, we have to now formulate how you can do it. Take the starting material which was the thiophene based starting material. We will do a series of reaction. The very beginning we will be doing a Korey-Czakowski reaction, which was already explained to you by a sulfonium iodide mediated epoxidation. So, this compound basically will give you this epoxide with this starting material, fine, and then this starting compound you react with MEmgBr, methyl magnesium grignard. So, it will basically give you OHMe. Now, this OHMe you basically convert this alcohol to corresponding chloride by POCl3, a standard chlorinating agent, that will give you the alcohol to chloride and methyl will be there, and then you treat pyridine as a base, you will basically get this compound. Okay. Now, this allylic sulphide is a very interesting precursor. If you subject this allylic sulphide with base, it will be generating this anion. Now, this anion will try to react with this epoxide in a sterically less hindered way. So, in next step you basically react these things, is not it, and then you try to react with this epoxide. This is basically reacting with this epoxide. So, what will get? This, and then you do the same thing, you treat with POCl3 and pyridine. Sorry, this is does not have the double bond, this is basically the single bond. This double bond will be now generated. Yes. So, this is the compound which was shown as a one of the intermediate here, same compound, the same compound. Okay. Now, this compound again you can treat with base butyl lithium, it will generate this carbon ion here, and here you reacting with this, as I said, called O lithium and this CH2 Br as a electrophile. So, this will attack here, and then what will get? You basically get the simple electrophilic addition product. Okay, the electrophilic addition product here, you can quench it with this. So, you are almost close, fine. You do this Raney-nickel treatment, Raney-nickel, hydrogen or ethanol. So, this sulfur cleavage will be there, this sulfur cleavage will be there, and then you basically get a ethyl group here, this part remains same, you basically get a hydrogen, same thing again. So, get this one which is our initial one of the intermediate. So, we are almost close, you take this starting material and you do a oxidation to get this corresponding carboxylic acid esterified with diazomethane. So, what you will get? You basically get double bond CO2Me. Now, there are 3 double bond, this is electron deficient, this is electron rich, this is electron rich. So, we will treat with one equivalent of MCPBA, one equivalent. MCPBA as we know is electron deficient oxygen. So, it will not touch this double bond, it will not touch, it may touch this, it may touch here, but definitely as I said this is sterically less congested, less hindered. So, you can expect that these things will be now epoxidized. So, this is your final product of the target molecule which we have earlier shown. So, this entire pathway basically gives you the juvenile hormone, which was the main target molecule. So, this is the target which have been achieved. The transformation which is used basically a reductive sulfurization as I said, and remember this sulfur basically acting as a temporary connection. reductive desulfurization we used, desulfurization, and as I said the crucial reaction is basically a this sulfur which we are basically removing. So, sulfur acting as a temporary connection. So, sometimes this is known as tether. What is tether? Tether is basically temporary connection, or temporary bonding, and this temporary connection was not required in the final target, and this was very useful by using a sulfur tether reaction, but eventually the reaction main reaction is reductive desulfurization, which will give you a very useful functional group assembly, and you can see that this final the target molecule was nicely achieved by using a reductive desulfurization chemistry. So, probably similar kind of things we will be explaining in subsequent lectures. So, till today just go through the reductive desulfurization technology, that how this reductive desulfurization method helps, or this sulfur tether chemistry helped to get access of some of the intermediates which is very useful in synthetic organic chemistry. And we have shown that this particular sulfur based tether is very useful method to give you a efficient target. So, we will be seeing in the next lecture. Till then, goodbye.